I'm so used to seeing two little beady eyes over Zoom for the last 2 years that it's kind of shocking to be back in a room full of people, but it's great to see everyone face to face for a change, and it's wonderful to have some of you here. But for about the next 15 minutes, I'm going to talk about the development of the PEER simulated ground motion database. And for those of you that came to the workshop in June 2021, that Hala had alluded to, I think you know that this is a high priority activity that PEER has great interest in. So what I'm going to do today is talk about the progress in the development of that database and how we're going to populate that database with the first realization of synthetic motions. And we're going to, within the scope of the PEER project, we don't have resources to develop real large models of the San Francisco Bay Area, for example. So we are going to leverage heavily in this project work that's being done for the exascale computing project for the Department of Energy, and I'll get into that. I want to acknowledge my co-investigator, Dr. Floriana Petrone, who is here. You'll hear from Dr. Petrone in a couple more presentations, and she'll actually give an example of some of the early applications of these simulated ground motions with respect to long-span bridges. We also have a graduate student, Parmita Ramani, and a postdoctoral scholar, Mahid Nia, who is working at UNR on this project as well. So let me go back and just briefly recap the effort from the PEER International Workshop in June 2021 and what came out of that workshop. I think this was a very successful event. We had 241 participants, essentially international from around the world, 41 presenters, and we had a great deep dive on the current state of practice with regional scale simulations in that workshop. We talked about all aspects going all the way from fault rupture, wave propagation through the earth, and interaction with infrastructure. We sort of covered technically that whole domain in day one. And in day two, we had breakout discussions. And I think those are very informative, and they actually informed this project, as well as the thoughts about where PEER's contributions in this area could be. And of course, PEER has a very strong focus on performance-based earthquake engineering. And so as I walk through this, you'll see that we have a premium in thought about how we use these ground motions, synthetic ground motions, for engineering evaluations in this project. One of the main principal things that came out of that, I'm indicating on the bottom, and we took a poll of all participants, was to identify a priority need to actually begin to create an open source database of simulated ground motions. And I'm going to paraphrase that maybe in somewhat extreme terms, but the discussion group said, we could admire this problem forever. Let's get going and create a database and start to populate that database and learn by doing. And that's exactly what we're going to do in this project. So as a follow-up to that particular meeting and that workshop, PEER, and I don't know how to close this up here. Sorry, it's in the way. I'll just move it down. So PEER created a simulated ground motion database committee to provide input and take polls and to sort of guide this. And you're seeing the people that are involved in that committee, and I'm sure you know a number of these. On purpose is a balance between earth scientists and engineers on that committee. And Dr. Petrone, you'll be hearing from, is the chair of that committee, but Pedro is on it, I'm on it. Morgan Machete and Arben Pitarka, two eminent seismologists involved in ground ground motion, are on it. E.T. and then Floriana. And now it won't advance. So the long view mission for that particular committee is shown here. Number one, that committee is going to help define the path forward for utilization and generation of these synthetic ground motion databases. So that's number one. Number two, develop a plan for characterization of uncertainties. Those of you that were at the workshop, you know there was one whole session on how do we characterize the uncertainties in these ground motions and propagate those uncertainties into some of our results. Identify compelling use cases, early use cases. This utilization of synthetic ground motions is in its infancy, as you probably know. Can we find a few really compelling cases that really demand utilization of very dense, for example, ground motions? If we're looking at distributed motions across a bridge or an infrastructure where having dense distributed motions is important, we'd like to identify some of those use cases. And then finally, a function that PEER often provides is to provide guidance on the appropriate utilization of these motions in performance-based earthquake engineering. And one could envision workshops and seminars surrounding that theme. The committee is also looking at what should the user interface for these types of motions look like? These are different than measured ground motions. There's a large number, as we'll get into, a very, very large body of records. You know, literally billions of records and surface motions we can get into. So how do we handle that? And so they are thinking about metadata, user interface, and things of that ilk for these. So that's sort of the purview of the committee. There are two concurrent projects going on in this area. And project number one is the PEER-SGD that we're talking about today. And the notion there is, you know, PEER has always been a leader in the development and the distribution of measured earthquake ground motions. You know, it's a logical extension for them to be thinking about becoming the purveyor and the distributor of very dense simulated ground motions. So that's sort of the motivation, overall motivation for this project. You know, we really need to leverage other activities in order to move this forward. And so I'm going to talk today at some length about the exascale computing project that's sponsored by the U.S. Department of Energy and centered at Berkeley Lab, where we will be utilizing the workflow as well as these new GPU-based accelerator platforms to do the very intensive calculations that are going to be necessary to propagate this and generate this database. So let me just define a little bit of that, and then we'll move into how we're using that. There's a workflow that's been developed over the last 5 years. It's called EQ-SIM for earthquake simulation. And we briefed this at that workshop in June. Essentially, we're developing the capability to go all the way from fault rupture, propagate those seismic waves through the earth, determine how they interact with infrastructure, and then come up with risk evaluations. And the purpose of EQ-SIM, as originally stated, is to really get a better understanding of the regional distribution of earthquake ground motions and damage by having very, very dense regional motions. And then secondly, how do complex, and I'll say realistic incident seismic waves interact with a particular piece of infrastructure. That's a second important component of that. And as many of you know, for many, many years, we've assumed one-dimensional site response with vertically propagating shear and compressional waves. That's not really true. And so what are the conservatisms or lack thereof of those? So that was really the driving forces for EQ-SIM. And EQ-SIM was built to execute and exploit the emerging GPU-based platforms that are coming out of the Department of Energy. That was the whole purpose over the last 5 years of why DOE actually funded that effort. And what I'm showing you here is the fact that, you know, we're there. We've been preparing for these machines for 5 years and getting the workflow ready. This is a plot showing the world's fastest ranked computer since 2000. What I'm showing you here, this new blue dot, is the brand new Frontier machine that is coming online at Oak Ridge essentially as we speak, and it's in final performance testing. So in the EQ-SIM project, we have access to a number of these GPU accelerated platforms that are helping us do unprecedented level simulations of earthquake ground motions. We're applying those in the San Francisco Bay Area, and we're going to leverage that set of simulations to actually help propagate and populate the first PEER database. In our workflow, there's 3 distinct components just to sort of set the stage for this. And what I'm building up to is how are we going to handle and manage all of these very, very large motion sets in an efficient way. Component number 1 is to develop simulation models, regional scale simulation models of ground motion. We're using the SW4 code, which is originally developed at Lawrence Livermore National Laboratory and has been advanced in this particular project. That's component number 1. Component number 2 is interacting those regional scale simulated ground motions with particular infrastructure that we care about. And so that's really where the performance-based earthquake engineering comes into this. Quite a few people are working on this problem, not so many people appropriately linking these models to fully exploit the ground motion. So that's a ripe area for PEER to be heavily involved in. And then finally, a relatively recent component that I'll mention if I have time is how do we deal with these very massive data sets? These are very, very large, very dense, as we'll see, and you really need to have special tools that really allow you to analyze those motions and understand those motions in an effective way. So if we stitch all those things together, a long story short, the EQ-SIM framework starts with a very, very large geophysics model. I'll show you an example of the San Francisco Bay Area, executed on accelerator platforms. Does very high fidelity ground motion simulations that's enabled by this new generation of platforms to get high frequency, resolve soft sediments in the near surface, very computationally intensive. Then the key is how do we store that data in an effective way so that engineers can fully exploit that data going forward. And I'm going to talk a little bit about that because this is a very, very important consideration for PEER, and I'll show you the challenges of doing that with some thoughts. Then, once you store that data, then the engineers can either do fixed-base structural analysis based on surface motions, or they can use DRM to look at soil structure interaction and the interaction between complex waves and the structure itself. The key to making this really work for the engineering community is, frankly, the data storage. We can compute these things now all day long, but we have to store that in an efficient way that engineers can actually exploit. So I'm just going to show you an example to try to drive this home. This is a computational model of the San Francisco Bay Area. You can see an earthquake hypocenter generated on the Hayward Fault. This is a 391 billion zone model that we've run on the Summit computer at Oak Ridge. You can see the waves propagating. These waves are coming here and interacting with the structure, in this case a 40-story steel moment frame building. And we have coupled and linked those particular simulations so that the structure is seeing the fully three-dimensional incident seismic waves, inclined body waves, surface waves, the whole 9 yards in that analysis. We're using open seas here, but we're not confined to that. We've connected this with Boris Eremich's code, easy, from UC Davis, so there's the potential for multiple different codes to utilize as long as they have an implementation of the domain reduction method. So these are the kind of calculations that one can contemplate. So what do these accelerated platforms do for us and why are they important? This is a plot of every San Francisco Bay Area ground motion simulation going back to the year 2000. You can see historically all of these studies, we were here, and then what has happened with EQSIM and these GPU accelerated platforms is here, and it looks like a hockey stick, right? Because they have really enabled going to very, very high frequencies, in this case 10 hertz, in a regional model, and just as important, the resolution of very soft sediments in the near surface of 140 meters per second, which is computationally very important. The other thing that's important for engineers is we have to move, and Norm Abramson, if you were at the workshop, he was a big advocate of this. Don't show me one simulation and claim victory, right? You really have to have the computational power to be able to explore the parameter space and do multiple realizations of this. This is really where these accelerated platforms have come into play as well. Not only do they allow us to do higher fidelity simulations, they allow us to do more simulations very rapidly. So for example, this computer Perlmutter that is at Lawrence Berkeley National Laboratory, we can now do one realization of a Hayward Fault earthquake at 5 hertz and a VSIM estimate of 250 meters per second, about a 30 billion zone problem in 9 hours. So we can run a Hayward Fault simulation overnight easily, and then run multiple of those as we're going to do for this project. I'll mention. So that's enabling. If you look at running these much higher frequency simulations, 10 hertz and 140 meters per second on the Summit computer, 391 billion points, we can do that in less than 2 days now. And so this is very, very important. Not only are we increasing the resolution of our models and getting frequencies of engineering relevance for the first time, not 1 or 2 hertz historical simulations at very long wavelengths, but realizations at 5 and 10 hertz. We can really compute those very fast. The frontier computer that we're about to jump on has just been ranked the #1 computer in the world. And so it is at 1.1 exaflops. That's a billion floating point operations per second. So if every person on Earth did a calculation every second for the next 4 years, that's what you would be able to do in 1 second on this computer. You kind of can't deal with these numbers anymore. It's getting amazing. But those are very, very important to this project because we are going to use those computers in that workflow to generate a suite of ground motions for the Hayward Fault that would be the first realization and propagation of this database. So we're in the process of generating 10 realizations initially of Hayward Fault events for different various rupture scenarios that we're going to get utilizing the Graves-Pitarka rupture model to 5 hertz and 250 meters per second. Why 10? Because if we look at the inter-event variability, just think of this simple simulation we have here in that location, we know that the ground motions at that site depend tremendously in the near field on the characteristics of the fault rupture. doesn't do us any good to look at one fault rupture. We have to try to span the space of many fault ruptures. And so we'll be propagating this database with this type of information. And I don't have time to go into it, but we're doing a lot of vetting of our motions. Last thing we want to do is create a database and put motions in there and have every engineer in the Bay Area calling us up and complaining and saying, well, look at this. So what we're going through very carefully and looking at our motions and building our confidence in those motions before we propagate them to the database. That's a very important element. The data set considerations are crucial. And so I just want to say there are things that are different in these simulated ground motion databases. Spatially dense ground motions, very, very dense. That 391 billion calculation at 10 hertz and 140 meters per second has a station in the Bay Area every 1.75 meters. So there's 1.3 billion surface points. That's a lot of data. We need to include multiple rupture realizations. Users must have a downsampling capability to effectively fetch the motions they want. You just can't deal with the 1.34 billion grid points. And I would argue, and I think this is important, the database design that we are thinking about must be concerned with future scalability for this. And I'll show that in just a second. So here's what we do. We do our simulation. We create an HDF5 data container. We have the possibility of compressing that data, and we have two options for saving the data. Just surface motions on the surface of the Earth through the Bay Area, or through a near surface volume so that we can come back and apply the DRM and interpolate to the boundaries of the local model. And so those are both schemes that we are accounted for. So this illustrates the challenge, and I understand this is a busy view graph in the time we have, but what I'm showing you is for the Bay Area simulations, for a 10 hertz, 140 meter per second simulation, this is what the data set looks like. If you save the whole data set here, 3.14 billion sites at 1.75 meters, there is 3.22 petabytes of data associated with that. That's not something PEER can deal with. To save that data and back up that data is just not in their wheelhouse. And so that's something that we will do in collaboration with Lawrence Berkeley National Laboratory. They've got huge computers and huge storage. They can do that. To get to a PEER manageable database, we're going to have to down select that data, downsample that data, and to get something that PEER can meaningfully share with the community. So looking here, this is the data storage currently in the entire PEER-NGA database of about 60 gigabytes and about 21,540 records. If you down select that data from these large runs, you can see that if we get synthetic ground motions at 1 or 2 kilometers or maybe a half a kilometer spacing, that's in PEER's wheelhouse. That's something PEER can deal with. And so going forward, this notion of scalable database, we absolutely want to save this because we don't know how we're going to use it in the future. We should save that and be just as careful about that as we are with real earthquake data, but PEER is going to have to develop a schema for downsampling and being able to utilize these smaller data sets. Just want to mention one more thing and then I'll get off the stage. Part 3 component of our work is actually some very, very nice software developed to be able to exploit and look through these motions because you have so many sites. So there's something called EQSIM Viz that was developed by a colleague, Hujun Tang, at Lawrence Berkeley National Laboratory. It uses a special server at Berkeley Lab to store these data sets, these very, very large data sets. And what that does is it pre-computes time histories and save those as PNG or JPEG files. And it's highly interactive. You can come in with the mouse and you can actually interrogate, click and point on a Google map background, and you can get the acceleration, displacement, and velocities to pop up. And in the spirit of ensuring that these motions are realistic, one can also compare those motions at that site with the site metadata in the ground motion prediction equations automatically. And so you will see the ground motion prediction equations pop up for that site, and you will be able to overlay the ground motions for that site, the simulated motions on top of that. So this is a whirlwind tour, but I really want to acknowledge the heavy leverage that we're doing in this project. We couldn't do it without the help from the national laboratories and the EQSIM project and DOE Exascale Computing Program. So the EQSIM contributors I'm showing here, and I'm sure you recognize a number of these, span all the way from computer science and mathematicians, because we have to make these big GPU platforms work well. And then, of course, we have some engineering content, but computer scientists and seismologists, really a multidisciplinary effort. So I wanted to work in the last slide and acknowledge them. So, okay, I'm done. Any questions at this point, Amarnath, or are we taking questions at the end?
Yeah, we can take questions now. I'll let you.
Yeah, any questions for David? We're really looking forward to the outcome of that, as it will put really PEER in a new direction that we haven't done before, which we thank David and his team for that. Any comments or questions from the audience?
Okay.
We're good.
Any comments from the?
I see something in the chat. Oh, no, there is just a general comment. If anybody online who have a question, you can put it in the chat, or
Anyone here?
Okay. Who's next? I will help them get their.
oh, I see Charlie has his hand up.
Yeah, a quick question.
Sure.
Yeah, please go ahead.
Well, thank you for the presentation. Very interesting. So, the natural question is, you have me drooling over this data. What is the availability of it now?
Well, the availability of it is we're still in the process of generating it right now. And the reason we're being careful, as I'd mentioned, is we want to do confidence building in those data sets before we distribute those.
Okay.
I think we're getting close. I think within the next 3 to 4 months, we will begin to have the capability of making these data sets available. Then it'll be an element of working with the PEER IT team to be able to begin to make these open source. And I think the discussions at the workshop were clear. We want to get these motions out into the hands of the community, both the research community and the practitioner community. That's our objective. DOE wants us to do that. DOE wants to see these motions used. So everybody wants that. I don't want it until we're confident that, we can stand behind these motions to some degree. And I'm sure people will discover things and give us a feedback loop. We welcome that. But we want to make sure we don't put things out that are, obviously incorrect and so forth. So we're doing a significant amount of confidence building in these motions. I'll just mention how we're doing that. We're looking at the numerics. For all of those motions in the San Francisco Bay Area, we're overlaying a spaghetti chart of all the spectra at every site to identify if there are any outliers that look untoward that we have to look at. Number two, we are going to run multiple realizations, and we're going to look at mean values of spectra at various locations and compare those with the ground motion prediction equations. It doesn't make a lot of sense to compare one-off time histories, honestly, with the ground motion prediction equations. And so we are looking at developing mean spectra at selected sites in the Bay Area, a bunch of control sites, and comparing those with the ground motion prediction equations as a confidence building exercise. And then finally, we are, and this is really the true validation exercise, we're looking at modeling a number of small earthquakes in the San Francisco Bay Area of magnitude 3 and 4. And we have a student from UC Berkeley, PhD student, who's doing that comparison, and that's really testing whether the code can replicate on a site-by-site basis for a well-characterized small source event the waveforms in the spectra. So we're doing all three of those things to build our confidence in the simulated ground motions before we begin to share and propagate those. Does that answer your question, Charlie?
Yeah, it does. Thank you so much.
Long answer.
Yeah.
Thanks, David.